All right, so we're going to do a couple of additional examples calculating work done by a variable force. So 7.5 additional examples. All right, so first one, let's do a lifting problem. We have a chain for this one. Very similar to the one we did in class. Just want to set another one up and show how we go through this. So we have a 20-foot chain that's laying on the ground, and it weighs 5 pounds per foot. We want to figure out how much work is required to lift it so it's fully extended. So I'm going to draw my picture. So in the end, my chain, I'm going to have it extended 20 feet. So my chain will be like so. So this is my chain. I'm not going to draw each individual link. One little piece of the chain, we call it delta. We'll set our y-axis going this way. One little piece of the chain, we'll call that, we could call it delta y or dy. Little piece of the chain, the distance that each piece is lifted is going to be y. And y varies from 0 feet. This piece that's down here at the bottom doesn't get lifted at all. And the little piece at the very top gets lifted the entire 20 feet. So, the weight of each section is the amount of force that it's going to take to lift that section of chain. So the force is going to be the weight per foot times the length, 5 times dy. And each little section dy is lifted a distance of y feet. So the work to lift that little piece is dw is 5y dy, and we're going to integrate that over the distance that each different piece is lifted. So the total work, is going to be the integral from 0 to 20, 5y dy. Nice easy integral to evaluate. 5y squared over 2 from 0 to 20, which gives us 1,000 foot-pounds. So we want to find the weight of a little piece in general, find the weight of a little piece of the thing that we're lifting. The weight of the little piece is usually going to be, we're going to divide it into small pieces, dy, we're moving it up. Find the weight of the little piece, figure out how far each piece is moved, and then evaluate the integral over the distance that we're moving our whatever the object is. All right, let's look at an additional pumping problem example. we're going to empty an oil tank this time. So we have a spherical tank. And it has an 8-foot radius. And it's half full of oil. And the oil weighs 50 pounds per cubic foot. We want to find the work done, or the work required to pump the oil out through the top of the tank. So let me draw a picture here of our situation. So here's my tank. And here we are in the center. Here's the surface of the oil. And we know the radius is 8 feet. So from the top to the bottom of the tank, we have 16 feet. I'm going to leave my units off here. What I'm going to do is set the y-axis through the center of the tank. And I'm going to set my x-axis along here. So we need to draw a picture, we need to define a coordinate system. Now we're going to draw a little disc of the oil, so a representative section of the oil. I'll do that in red. So here's a little slab of oil. It's here in the tank. And we'll go back here like so. And we're going to call this thickness, the thickness of this little slab, dy. And we're pumping the liquid out through the top. So the height of this little slab of liquid above our origin is going to be y. So we're y units up from the origin, and we're pumping it out through the top. So this slab is going to be pumped a distance minus y. So at the surface of the oil in the center of the tank, y equals 8. 16 minus 8 is 8. So this little slab that's at the surface of the oil is going to be pumped 8 feet. And at the bottom, where y equals 0, this little tiny little piece that's sitting right here at the bottom of the tank is going to be pumped the entire 16 feet over the top. That's how I check to make sure I've set everything up correctly. So our disc, our slab of oil, has a thickness dy. And its radius is some quantity x. So from here out to here is some x value. Our radius varies as we move through the tank. So we're going to have to find an expression for the radius in terms of y. We want to integrate in terms of y, so we have to find an expression for our radius in terms of y. So the force that's required to lift this slab of liquid, this disc, is the weight of that liquid. So its weight of the slab is the density, 50 pounds per cubic foot, times the volume of this disk, which is pi x squared. The radius of that disk is x, times its thickness, dy. And our units are going to be pounds. So pi x squared is the area of the circle times the thickness gives us the volume of that slab times its density gives us the weight of the slab. So we need to come up with a method of expressing the radius, this x that varies as we pump this oil. We need to find x in terms of y. I can do it a couple of different ways. At the surface of the oil, so let me write here, we want to find x, radius, we want to find the radius x in terms of y, so we can integrate with respect to one variable. At the surface of the oil, I have a circle here, circle of radius 8. And its center is at 0, 8, based on my coordinate system. So I'm going to write the equation of that circle based in my coordinate system. So I'm going to say x squared plus y minus 8 squared equals the radius squared. And I can rearrange this, multiply this out, and I solve for y, or sorry, solve for x squared. We need x squared in my integrand. So I get x squared. When I expand this and simplify, x squared equals 16y minus y squared. The other way that we could look at this is if I draw this circle. I'm going to redraw this. Here's my slab of liquid that we're looking at. I'm just going to draw that. Let me just draw it as a circle, just edge on. So my slab is here. Here's the center of the circle. I'm going to draw this right triangle here. So I'm just looking at this edge on. So this distance is the radius of the circle. This is x. This is the radius of the tank, which is 8. And if this distance is y, this little distance is, this little piece, this side of the triangle, is 8 minus y. And then I use the Pythagorean theorem on this triangle. So 8 minus y squared plus x squared equals 8 squared, and I rearrange this and I get the same thing. So this leads me to x squared equals 16y minus y squared. Either way of looking at it leads me to the same expression for x squared. So now I have an expression for the square of the radius, which I need for my weight in my integrand, in my integral for the work. So each slab of liquid is moved through a height of 16 minus y, as y varies from 0 to 16. So now I'm ready to set up my integral. So the work is going to be the integral from 0 to 16 of the weight of the disk, which we decided was 50 pi times the radius squared, which we came up with 16y minus y squared, times the distance that we're moving that, the weight. We also have a dy here, I'm going to put that at the end, times the distance we're moving that, and there's the dy that goes with for the thickness of our slab. So 50 pi times 16y minus y squared dy is the weight of the slab. We're moving that slab 16 minus y units. And we integrate this. So I can expand this out, so I get 50 pi, multiply all this out, 256y, not a difficult integral to evaluate, minus 32y squared plus y cubed dy, and I evaluate that integral to get my work. Now I realize, now looking back, I realize that the tank is half full, so we don't integrate from 0 to 16. The tank is half full, we only have to integrate from 0 to 8 because the tank is only half full. So let me go back and change my limits. So 0 to 8. The tank is half full. We evaluate this integral from varying from y equals 0 to 8, and we get that it's approximately 589, 782, foot-pounds. So again, in general, with pumping problems, draw your picture, set up a coordinate system, make the coordinate system nice so it's easy to use. When you can set the origin, so that gives you some nice symmetry, that usually is a little easier. Divide your liquid into little discs, little slabs. Find the weight of the slab. The weight of the slab is the force that it takes to move that slab, to lift that slab. And based on your coordinate system, decide how far each of those slabs is moving, and integrate over the liquid so that you get each piece of the liquid, each slab of the liquid, moving the proper distance that is being pumped. And in problems where the size of the disc varies as we move through the tank, we have to find an expression for the volume of that disc that involves only the variable that we're integrating with respect to. So in this case, we wanted to integrate with respect to y. So we had to find the volume of our disc to get our weight only in terms of y.